This video is going to cover Chapter 6 in Engineering Problem with Solving with C, and we're going to be talking about programming with pointers. Which kind of pointer? Lots of pointers there. So anyway, before we do that, I'm going to go back to a presentation I did early on in Chapter 1, I think, which talks about the internal organization of a computer. And the reason I'm going to do that is because we need to understand how data is stored in the computer and how things have addresses inside the computer. So you have your microprocessor in the middle of the computer, also called the CPU for Central Processing Unit. And this microprocessor can talk to your internal memory, like your RAM or your ROM, and also the microprocessor has some internal memory itself. So some of it is some local memory that it has so that it can do operations very quickly within itself, and then it also has a thing called registers inside, which are maybe like individual memory locations where the microprocessor works on a particular instruction and puts data there and works on the instruction right here. So what we've been doing, is writing software. We write source code and it gets compiled, which means it turns it into machine language and is stored inside the computer. So just to remind you of this different layers of software that we have in a computer, at the very middle of the computer you have hardware, and in your hardware, in your memory, in your central processing unit, there are literally millions of transistors that are either set to be turned on or turned off. And when the transistors are turned on or turned off, this represents ones, or we symbolically say 1 or 0. 1 is on, 0 is off. And big sequences of 1s and 0s ends up making bytes, and bytes make words, and so forth and so on. But that all resides down inside the hardware of your computer. And next you have the operating system. And when you develop the operating system, you do it with a very low-level language. C happens to be a language that you can make operating systems with. And then above that you get fancier programs that are in the higher level you get, the more human readable they are, such as Python. Python is a very easy language to read. C is pretty close to machine language, and I will show you that today. So just a little bit more of a review from Chapter 1 that I did. This is a little piece of C code, and when it gets compiled, it gets turned into machine language. And machine language looks like this: sequences of 0s and 1s, but this is actually written in hexadecimal. And so instead of saying all 0s and 1s, which is a base 2 system, a binary system, we actually convert the binary numbers into hexadecimal numbers. I don't know whether it's fair to assume that you in this class know how that's done. A lot of people in this class already know how. If I need to do a lesson on converting between binary to hexadecimal, I can. No problem. But suffice it to say that these are all hexadecimal numbers which translate directly. It's base 16 numbering system, which will translate directly into a binary number system. So this binary stuff, actually in hexadecimal, is not very easy to read. So what we humans do is look at the binary and assign some kind of it's called a mnemonic to the binary, and so that it becomes more readable. So it's symbolically showing what the binary means. So I'm going to show you today that we can take our C code, and I'm going to show you how it disassembles into the binary numbers that are stored in your computer, and I'm going to show you how it sits at a certain place in memory on your computer. And I will also show you this slightly human readable form of the language in these 3 phases. So remember, we write our C programs in an application such as Notepad++. That's our source code. We compile it. We're using a compiler called GCC. It's an open source compiler that we're using. And then that compiler converts it to the object code. And the object code literally looks like a stream of 1s and 0s. Then we have to For example, we have preprocessor directives. Maybe we make a function call to a printf function. So we have to link those things together. So there is actually a link and load statement. But the load is actually taking the machine language and sticking it somewhere in memory, and then we can run the program. So I am going to show you that today, all the way down to the machine. I'm going to show you how you can actually look at where the program is stored in memory and what it looks like all the way down to binary form. So just one more little reiteration of what I just talked about. You have your CPU right here, and what it actually has to do, it has to go out somewhere in memory, in RAM most likely, unless you're booting up and then it's in ROM. But if you're in RAM, if you have memory, something stored in memory in RAM, each one of these little binary sequences corresponds to some instruction to the CPU. And the CPU has to go out and get an instruction, bring it into the CPU, and do what the instruction says. So it might go out and get an instruction, come into the CPU, the instruction says go out in memory, get a number, bring the number back into the CPU, add it together, or do some other operation. So the CPU has to know where to get the instructions. It actually goes through the instructions sequentially until it jumps somewhere else. So each one of these memory locations has an address associated with it. So right now, simplistically, I show that the address of this data is 0, and then 1, and then 2, and then 3. Of course, that's 0, 1, 2, 3 in a decimal system. So the instructions are all in memory. Our source code gets converted to binary, and it gets put in memory somewhere. But each instruction has to sit at an address. If you're more interested in this, in fetching instructions and bringing it into the CPU process, I put a nice little link down here that has a good illustration of this. If you take a microprocessor course, you will learn about this in detail. That's on my campus. That's an ETRO 280 class, a microprocessor class. But if you take an assembly language course or a microprocessor class, you will learn about this sequence in detail. So moving on ahead, we can actually see what's inside the microprocessor as it executes our program. But to do this, we have to download a program from Cygwin, and it's called the GDB, which is the GNU debugger. So we have to download a program, which is going to be a process similar to exactly how we downloaded the GCC compiler. And so we can download the associated debugger, which is called GDB, and we can look at what's inside the microprocessors. And we can also look what is in memory. So we can look in memory at where our program is stored and see it. So that's what we're going to do next. We're going to look at memory, and we're going to look at registers and memory that are inside the microprocessor, and we are going to see how our a little simple piece of C code gets stored into our computer. And the reason that we are doing this is so that we can understand pointers, because pointers are locations in memory that store an address that we need. And I want you to be able to understand what's happening with pointers. So to get the GNU debugger, which is called GDB, you go back to cygwin.com, which is where we got our GCC compiler, and you rerun setup.exec for your 64 or 32-bit machine, whatever you have. These are just snapshots of going through the instructions that you've seen before. You have to choose a download site, choose any one that you want. Doesn't matter if one of them doesn't work right, it's too slow, stop it and get another one. And then you get to this place where you have to select the packages that you need. If you just search for GDB, it will come up. So there I see the GDB debugger. I select that, I install it, you are done. You do not have to change the path anymore, because GCC is already installed and it knows where to find it. So you don't have to do anything with your setting your path in your machine. So next we're going to talk about using this GDB, assuming you now have it completely installed. So So, how to use the GDB or the GNU debugger. This is the example that I'm going to do. It's a extremely simple little piece of code. Includes standard I/O. I don't even return 0 here, so I have a void main function. And all I want this function to do is make a function call to printf and print an asterisk to the screen. So we'll compile this very simple code, and after compiling it, the source code is converted into binary and stored into memory location. Oops, I wrote binary is easier to read in, yeah, binary is easier to read in hexadecimal. So we're actually going to see it in hexadecimal, and I'm going to convert it to binary for you. It's even easier if you associate the mnemonics with it, which I'll show you in a moment. So we want to see what it looks like in memory, and we want to see where and how this code is actually stored in our computer. So in order to use the GDB debugger, the GDB, you have to compile your code. My program is called simple.c because it is so simple. But you compile with this kind of a statement, GCC, and then you have an option -G, which means I want to use the debugger. And then the rest of the compilation statement is the same. You run the program just the same as you did before. But then when you want to enter the debugger, you say GDB and then the name of the program. So I am going to do. So I see my everything that's in this directory right now. So I'm going to say gcc-g simple.c-o for make the object code, and then I'll call the final program simple. So I'm compiling it with that extra option with the -g in there so that I can use the debugger. I can check and make sure that my code actually runs like I think it does. Yes, I guess I have no new line there, so I just outputted the asterisk like I expected. Now let's look at the debugger. So gdb simple, and then the debugging program will load. So here's where you'll learn a few things about it. So if I just want to look at the code at this point, I can type list. So there it repeats the actual code that the source code. So what we want to do is we want to find out where in memory this source code is sitting. Notice that I have lines, it gives me lines 1, 2, 3, 4, 5, 6 right here. So I'm going to issue a command to set a breakpoint in the code, and the way you do that is with just type a B and space. I'm going to break at line 1. I'm going to do a break right at the beginning of the program. So B space 1, enter. So it says I've made a breakpoint, and here is our address. This is in hexadecimal, so 0x means it's in hexadecimal. I have a breakpoint at this address, and it's in this file, and it's line 1. In case that was hard to see, I think you can see it all. I did a clip of it and put it back in the PowerPoint. Notice that after I do a list, I can see that the code starts at line 1. So moving on. Then I did a break at line 1, and I was able to see where in memory my program is going to sit. Line 1 is going to be sitting at this address. So my next step here is going to be to disassemble the code. I'm going to show you the disassembly statement, and then I'm going to come back to this PowerPoint and point some things that I have highlighted out. So the instruction that you need to say is disassemble. So D-I-S-A, S-S-E-M-B-L-E, disassemble. And I want to disassemble starting at the address where the code is. So I'm just going to select it, right click, and paste it there. So I'm going to disassemble my C language code, and it's going to be converted into assembly language. So let's show that to you. So there it is, converted into assembly language. So it looks a little bit different, but we can recognize a few aspects of it. Like, for example, there is a main. Instead of printing an asterisk, it looks like it actually underneath is calling the put character function. The other thing to note, this is all of the addresses. This is the address for what this is in memory. But it's written right now all in assembly language. So let me move on to my PowerPoint here. So I'm going to highlight a few things. Here is the disassemble command that I used. This part in yellow right here is the addresses of everything in memory. So my program is sitting between these addresses in memory. This is all in hexadecimal. So remember, our program did one thing. It did one thing only, and that was print an asterisk. So an asterisk in ASCII is 2A in hexadecimal. So the ASCII code for an asterisk is a 2A. And if I look up here, this is assembly language now. If I look up here and kind of some things maybe you can pick out. For example, we know that this represents the function call to main. Main is actually a function. Here's a function character to put character, so that will put the asterisk out onto your monitor. And there's the value right there, 2A, that's actually going to be put out onto your monitor. And then there's a return at the end. So you can sort of see that our C code is sort of embedded in here into this assembly language code. These are registers. These are things are registers inside the microprocessor, and I can show you what those look like too. Here this line is moving an actual value 2A into a register right here inside the microprocessor. Take an assembly language course and this part will have a whole lot more sense to you. But what I wanted to show you was, this was our code, and here's how much memory it takes up. Not very much at all. So I can highlight that section. What I did next was, let me show you how I got that for a moment. So back to here, I can see there's my code right there. So there's some options that we can do with the disassemble command. Here's disassemble, and I'm going to do a /R, which is an option, and put the same address right there, starting address right here. The /R option means show me the binary. It's going to show you in hexadecimal, but it's going to show it to you. Instead of having this human, believe it or not, human-friendly, human-readable assembly language, it's actually going to show you the binary. Well, it's going to show you it in hexadecimal. So here we go. So, for example, this move command in assembly language translates to 4A89E5. And that's in hexadecimal. So this is 1 byte, 2 bytes, 3 bytes of information right here. This line right down here, I can see where I'm putting 2A in a register, and it's another move command, but you can see it's moving into a different register. But I can see right here the hexadecimal sitting in memory, and it's at this address right here. Actually, this first byte, the address of 55 is right here. The average of 48 is 1 byte later on, so that's what this +1 means. And this is the address. So here the address ends in E0. Now the address ends in E1. So this line of information here took 3 bytes of information, so now I'm 4 bytes from the start, and this information is going to start at this address in memory. So this is a little confusing, but what I wanted to show you next is that this hexadecimal, I'm going to show it to you broken down into the binary. I'm going to break down this address into binary, and I'm going to break down what's stored at that address in binary. Which I had to do, I couldn't do with the GDB program. I had to do it manually, and I did go ahead and do that. So I will show it to you. So this is the hex information that I'm going to go ahead and convert to binary. And you can do that with your Windows calculator in scientific mode. You can convert decimal values into binary values into hexadecimal. So the first line of our program, our little simple C program, started out with a 55, which was a push command in assembly language. 55, we give it the mnemonic called push. So it's actually probably pushing something on a memory stack or in a cache of memory somewhere. So 55 in hexadecimal is 1 byte, and that means it's 8 bits long in binary. So 55 is stored at this address, and I wrote down that big hex address. Now I have a 64-bit machine, so this hexadecimal address takes 64 bits to express in binary, and so there's my 64 bits that expresses this address number. And you can continue. The next instruction begins with a 4-8. I can translate it into binary. It sits at this address. I can translate that address into binary, and as you can see, it gets rather tedious as I sift through memory addresses, and what's at the memory address is right here. This is what's at the memory address, and this is the address right here. I can even come down here to where 2A is. 2A translates to this number in binary. 2A is in hexadecimal, and that's the ASCII code for an asterisk. And I didn't write its address down. I was getting tired of transferring gargantuan hexadecimal numbers into binary. But that's where it's sitting in my computer. So I'm just going to look at that one line just a little bit closer. This is where we were moving an asterisk, the value for an asterisk, which was an ASCII 2A, into a memory location somewhere, or actually into a register somewhere. This was the actual hexadecimal instruction right here, for, which we assigned the human readable mnemonic for it, because move is a little bit easier to read than B92A000, right? So this is in hexadecimal, and this was the address where that instruction is located, also written here in hexadecimal, but would turn into 64 bits long if I wanted to see it in actual binary, which represents 64 transistors either turned on or turned off. So if you are intrigued with using the debugger, here is a kind of a nice reference about using the GDB debugger. So it's a GDB tutorial right here. That's the table of contents, and you can learn more about using the debugger. So one last thing about using the debugger, I actually think that move 2A is either going to a register or coming from a register. I don't remember which, but at this point. But I can show you the contents of what's in registers also, and how you do that is say info R. Oh, the program has to run. So run. It'll run to the first breakpoint, and then I can say info R, and these are all the registers, flags, program counters, and everything that's associated with the microprocessor that's in my computer. Now, you might have a different computer, or you might have a Linux system, and your registers will have different names than my registers do. The registers all begin with R's right here. So I can see what's in the registers in hexadecimal, and here it is in base 10 or decimal. And if you were taking a microprocessor course, you could sift out what some of this means. One thing I will point out is that some of these internal registers have some addresses stored in them that we will see why that's important here in a little bit.